Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 10 of a unit electric charges and fields. Today we are going to discuss about the applications of Gauss's law. If you have gone through the previous classes, we have done up to the Gauss's law, their proof and their applications. Now let's begin with the first application of the Gauss law. It's an electric field. It's an electric field due to a point charge. So let's begin. Let us suppose a point charge is there, which is having a value of Q, and I need to find out electric field due to point charge using Gauss law. So what I can do is, let's say I want an electric field at this position. This is point P, and it is separated by charge Q by a distance of R. So what I need to do is you need to create a Gaussian surface which can cover this point. So if I make a Gaussian surface something like this is a Gaussian surface that I have made a sphere having radius r. You always need to consider one thing, that at whatever the point you require an electric field, you need to create a Gaussian surface such that that point should be enclosed within the Gaussian surface. Now, now what you can do is, you know that flux is equals to surface integral of E dot ds, and one more relation using the Gauss law. It's a flux is equals to Q enclosed divided by epsilon naught. So you have two options. One is the surface integral of E dot ds, and another is the Q enclosed by epsilon naught. You are going to compare this two. So first, let us begin. Let us begin with the E dot ds. Let's look up any arbitrary point. I will take this point, and at this location, I need to find out the direction of electric field. What is it? Tell me. It's a plus Q charges. We have learned this in electric field lines or electric lines of forces, that when plus Q charges will be there, the direction of electric field will be radially outward. So this would be the direction of electric field. Very good. Now what would be the direction of area vector? We say it's an perpendicular. It's a perpendicular and outside the surface. So for this position, the direction of area vector would be in this. So if I look at the angle between E and ds, it is a zero. So, the situation seems to be that flux is equals to, or I can write this as d phi is equals to sir E ds cos of 0 degree. And when I consider, sorry, when I consider a cos 0, it would be E dot ds. This is d phi. Now, if I integrate this, both the sides, then this would be a phi, and this would be E multiplied by integration of ds. Integration of ds, it would be an integration of this kind of whole surfaces, which will give me a sphere, and the area of a sphere, or rather I say surface area of a sphere is 4 pi r square. So this E multiplied by 4 pi r square, this should be the flux. Let's say this is relation 1. Now, what you need to do is, you need to put this value in relation number 2. If I write this is Q enclosed by epsilon naught, and this flux is equals to E multiplied by 4 pi r square, should be is equals to Q enclosed by epsilon naught. Is it done up till now? Okay, let's look what happened next. So the things are E multiplied by 4 pi r square should be is equals to Q enclosed divided by epsilon naught. So this E would look like it's an Q enclosed divided by 4 pi epsilon naught into r square. Can I write like this? Now Q enclosed is Q itself. So this is Q divided by 4 pi epsilon naught multiplied by r square. If I replace this 4 pi epsilon naught by a k, it would be an E should be is equals to kq by r square. This is the electric field. Now, do you have you seen this before? Yes, in very beginning of the classes, when we define an electric field, we have said that E is equals to kq by r square for the point charge. Here we have derived the same. Here we have derived the same using the Gauss law. So now we can use a Gauss law because it will give us a correct result. That is for sure. So this is electric field due to point charge. This is electric field due to point charge. Okay. Where where r is the distance. R is the distance from point charge. Now the relation says that E directly proportional to the 1 by r square. That means as soon as distance increases, electric field decreases, and vice versa of this. Are you able to get this? Well then. Next, let us suppose if I want to plot a graph for electric field versus a distance, how it should look like. Tell me. Look at this. As soon as distance is going to increase, electric field will decrease. As soon as distance is going to increase, electric field decrease. So the things would look like this. Please make a point that it never touches a zero. It never touches a zero. So the curve should look like this. This is electric field versus distance. So as soon as distance is increasing, as soon as distance is increasing, your value of a field will be decreases. Are you sure? Yes? Any doubts? No? Let's move on. Next, second application. It's an electric field due to a charged spherical shell, conducting sphere, and non-conducting sphere. But before we move on, consider a one thing that the relations or the formulas for the charged spherical shell and conducting sphere would be the same, while we derive differently for the non-conducting sphere. But up till now, it's an whether it is a charged spherical shell or whether it is a conducting sphere, the things would be the similar. Now let's begin. That we are starting with the electric field due to a charged spherical shell and conducting sphere. What we have given is that we have considered a charge. Let's say this is the situation. We are having a spherical shell of radius r, and that shell is given a charge q. We need to find out electric field at a point p at a distance r from the center of the cell. Let's say this is the location p, and the distances are where you need to find out the electric field. Are you okay with this? Okay. So let's begin. Find out the surface charge density. If you remember this, we have defined it as an Q divided by area. Area of the sphere. Area of the sphere, it's in 4 pi r square. So that comes to a sigma is equals to q by 4 pi r square, and that q should be is equals to 4 pi r square into sigma. Okay, now now when we want to find out the electric field at outside the object, so this point, this is the location r, this is the location r, and we need to find out the electric field at point P, which is greater than R, which is greater than R. So the situation would look like that. This is my sphere. Here charge Q is given. Here charge Q is given. And this radius would be the R. This radius would be the R. And I required an electric field at certain point, which is beyond this. So how I can do this? What was the situation? Did you remember what we have performed? What we have performed in calculating electric field due to a point charge using Gauss law? Do you remember this? Have you? Yes, what we have done is we are going to repeat the same thing. We are going to repeat the same thing. Let's say this is the sphere, radius r, charge q. I require an electric field. Let's say at this point, that this point, the distance from point charge, it's an r. You need to create a one of the Gaussian surface, and you need to enclose that point at which you require an electric field. Now, what is the next step? What is the next step? Yes, you are right. Here you need to assume a certain surface. Direction of electric field would be in this. Direction of area vector would be in this. So when both are equal, theta in this situation would be a zero. Theta in this situation would be zero. Now you need to do is flux is equals to surface integral of E dot ds. If I integrate this, I will be having E multiplied by 4 pi r square. Another relation that I know is the flux is equals to Q enclosed divided by epsilon naught. This is my relation number one. This is my relation number two. Now I am going to compare this two. This is E multiplied by 4 pi r square. This is equals to Q enclosed of epsilon naught. So this is electric field. It's an 1 upon 4 pi epsilon naught into Q by r square. This is the situation when r is greater than r. I am talking about the distance which is beyond the radius, which is beyond the radius of a given sphere. Are you sure? Okay. So let's look at the one more case. Basically, what we are supposed to do is we are going to find out the electric field at three locations. This is first. The next location would be at this point. This is our second application. We have done this. And for the third location, we are going to choose this point, this distance. So let's begin with the second location where electric field required would be at the top of the surface. That when the point P is on the surface, when point P is on the surface, what should you do? Tell me. We are going to derive just for once. Let's say this is Q having radius R. Now, in this situation, you require an electric field. You require an electric field when point P is on the surface. So what you need to do is you need to cover this by a certain Gaussian surface. And at this point of time, I'm going to take a Gaussian surface as a sphere as well. And even the radius would be the R. So what you need to do is assume a certain cross-sectional area, make a direction of electric field, make a direction of area vector, that theta would be a 0 degree, that theta would be a 0 degree. So this is flux is equals to surface integral of E dot dA. Angle would be a 0, so this will give me a E multiplied by 4 pi r square. And what I can write is flux should be is equals to Q enclosed divided by epsilon naught. So if I compare this to that E multiplied by 4 pi r square should be is equals to Q by epsilon naught. So this E stands to Q by 4 pi epsilon naught into R square. Now I can write this by one more unique way. That is the E that I know that sigma should be is equals to Q by A. And for area, it's a Q by 4 pi R square. Yes. So I can write like this. E should be is equals to sigma. E is equals to sigma by epsilon naught. Or you just remember this things. E is equals to K Q divided by R square. This is the situation. This R square is at this position. Please do not get this confusion. Clear? Are you sure? Okay. So we have done two tasks. We have done two tasks. Look at this. We have done this. Now we have completed this too. Now our task would be to do this. That electric field at a point which is within the surface. Where point P is inside the object. What you can do. What you can do. Let's assume that my location is this. This is point P, and this is in this situation R is less than R. That is, it is within the surface. So what I will do is I need to perform the same task. You need to first create a Gaussian surface that I already created. This is my Gaussian surface. Then I need to find out the electric field and area vector. This is the direction of area vector, and this is the direction of electric field. So angle between these two, theta would be a 0 degree. Now what you can do is you can write it down. Flux should be is equals to surface integral of E dot ds. So when I do this, it would be an E multiplied by 4 pi r square. Now you are comfortable with this. Next, I need to perform flux is equals to Q enclosed by epsilon naught. Now tell me one more thing. Very important. Think it very carefully. What should be the value of Q enclosed? What should be the value of Q enclosed? Consider one thing. Let us suppose you have given a charge Q here as well. But charges are having a property that they will like to be on the top of the surface. That means they will arrange themselves on the surface of an object, whether it would be a sphere, whether it would be a shell, or whether it would be a ring. They would look like to be on the top of the surface. So if you have given a charge q here as well, they will travel and move to this surface. So if I consider the situation, whatever the charge you have given, that was present over here, that has been moved here, moved where? Moved on the surface. So if I consider this Gaussian surface, what is the charge enclosed? Yes, absolutely right. It is a 0 divided by epsilon naught. So that ultimately comes to a 0. So electric field inside the conducting sphere or spherical shell is a 0. E would be equals to 0. So do remember this thing. Field inside spherical shell is always 0. Now, can you recollect this? Can you recollect this from the properties of electric field lines? Did you remember the properties of electric field lines? One of the property were One of the property of electric field lines were that they never enter metallic surface. This could not be the situation. Why? Because electric field inside a sphere or inside any metallic object would be a 0. This is the reason that this kind of electric field lines were not available. Yes, yes, everything is linked. You need to revise this unit from a very beginning before entering to the any new session. This will help you because this is a very longer version of an unit. Basically, electrostates have been divided into two segments. First is the electric charges and fields, and second is the electric potential and capacitors. Both the units are very lengthier. That's why I have divided this lecture into a small sections so that you can have a practice as well. But this purpose will be justified when you revise this from a very beginning every time. Please do this. Please do this. When I send a video, you should make a class note of it. You need to revise the class notes. You need to perform a numericals based on this, and then things would be easier. But there are more chances that you will forget something, certain data, certain tricks and techniques. And only one option with you is you need to revise it. You should remember class notes very, very particularly. If you know the class notes, if you know the each and every points of a class notes, things would be easier and things will be done for sure. But if you don't remember this class notes, thing would be typical for you guys. So please, it's a request that go through class notes very carefully. Go through video lectures very carefully. Do not skip any of the slides. If you are going to skip this, you are not going to have a logic behind it. So please don't do it. So we have discussed 3 points. We have discussed 3 points. That one, when point P is outside the sphere, which is R greater than R. Second point, when point P is on the sphere, it's an R equals to R. And the last point, it is the when P is inside the object, it's an R less than R. We are having a relation of E is equals to QQ by R square in first two cases, and in last case it would be an electric field would be a zero because charge enclosed will be a zero. Have you done up to this? Any query, any concern, anything? No? Okay, let's move on to the next. Now they have been asked that electric field due to non-conducting sphere. Up till now it was the conducting sphere. Now it is non-conducting sphere. Basically, tell me what is the difference between conducting sphere and non-conducting sphere? What would be the difference? Let's say I have taken two surfaces. First is the conducting sphere and another is the non-conducting sphere. First is the conducting sphere and another is the non-conducting sphere. Let's say you have given a charge plus q at this point. You have given a charge plus q at this point. Look at this. This is conducting sphere as it can conduct. In previous slide only we have discussed that charge likes to be at top of the surface. So this charge will move to the surface and this charge would be available at this location. And at center of the sphere, whatever the charge were, that has been transferred to the top of the surface. This total charge would be a q. Now consider the second situation. As it is a non-conducting sphere, it is not having a conducting path to travel from center to its surface. So what happen would be it will arrange themselves within a sphere itself, where it would be aligned how much that we can calculate by a unitary method. But we are sure that this charge would be completely not available on the surfaces. So even within a sphere, there must be certain charge enclosed. While I am talking about the non-conducting sphere, Do you understand up till now? Are you sure? When conducting sphere will be there, that whatever the amount of charge you given at, whether you have given it on the surface or whether you have given it at the center, both in both the situations, charge will be available at the surface of the sphere because it is having a conducting path. But for the non-conducting sphere, you are not having a conducting path. That's why it has been called as a non-conducting. So charges would be available even at within the surface, within the body of a sphere. So now again we are going to start with a certain unique approach. Let's say this is a non-conducting sphere. This is its radius r. We have given a charge q here. We require electric field at these three locations. It is the same that we have done. First location would be at this. This is r, and I can say this is r greater than r. Second location would be at this, which is equals to r equals to r. This is my second task. And my third task would be at this location. This is r less than r. This is what I need to do. I need to perform an electric field. I need to find out an electric field at these three locations. First, it's an outside the surface, which is r greater than r. Second, on the surface, it's an r equals to r. And third, within the surface, it is an r less than r. So let's begin. When point P is outside the object, when point P is outside the object, let's say this is charge Q having radius r. This is charge Q having a radius r, and this is the location. This is the location where you need to find out electric field. So again, you are going to do the same thing. This is dA, this is E. Now you know that this electric field, this electric field will look like this. E is equals to kq by r square. Here, if I make a little correction, I replace this by r because we have written r for the radius. So this is electric field would be equals to kq by r square. For which it is for the location when it is available at outside the object. Have you done with this? Are you sure? Okay, let's look at the next. When the point P is on the surface, this would be the situation. This is charge Q having radius r, and you require to find out the electric field at this location. This is R equals to R. So if you replace the relation in previous sections, we have having a relation that is E is equals to KQ by R square. If you replace this, it would be an KQ by R square. This is the same relation that we have received in conducting as well. This is the same relation that we have received in conducting as well. So that should be is equals to E would be is equals to E would be is equals to KQ by R square. Have you done up till now? Are you sure? Will you be able to solve this? Will you? For sure. Okay. Now let's look at the third and very important that you need to find out electric field for the non-conducting sphere when R is less than R. When R is less than R. First task would be to find out this Q dash. First task would be to find out this Q dash. How could you do this? How could you do this? Can I write that this charge we is available within the complete sphere having a radius of r? So we have one terminology that we call as a volumetric charge density. It was the rho which can be written as q by v. So if I write this charge as a capital Q, then this would be available throughout the sphere. That means 4 by 3 pi r. Now, even in this Gaussian surface, the charge density I mean to say a volumetric charge density remains the same. So if I write like this, it's in rho is equals to q dash divided by v dash, then I can write as it's in q divided by the value of it is q dash divided by 4 by 3 pi into our radius. It is a small of r. It's 4 by 3r. Now, as I know that volumetric charge density would be the same throughout the sphere, so I can compare this two. So the things would look like q by 4 by 3 pi r cube should be is equals to q dash divided by 4 by 3 pi r cube. So this 4 by 3 pi would be the con, and q dash should be q multiplied by r cube divided by capital R. This is charge enclosed. This is charge enclosed. It is the only new task. It is the only new task. Other tasks would remain the same. Let's look. Consider the Gaussian surface. This is our Gaussian surface. Consider the area vector. This is our area vector. Consider the electric field. This is my electric field. Theta between this two, it would be a zero. Now, what would remain? So let's begin with this. That phi phi is equals to surface integral of E dot dA. Phi is equals to surface integral of E dot dA. And when I write this that it is a surface integral of E dot dA, it should be E multiplied by 4 pi r square. E multiplied by 4 pi r square. I know that flux is equals to Q enclosed by epsilon naught. Flux is equals to Q enclosed by epsilon naught. And what is Q enclosed? I need to check it. It's in Q multiplied by R cube divided by R cube. That is Q multiplied by cube of the distance divided by cube of the radius. Now I need to just compare this. Now what I need to do is I need to just compare this to. And if I compare this to, I can have E multiplied by 4 pi r square should be is equals to q into r cube divided by r cube. So the things would be E would be is equals to q multiplied by r cube divided by r cube and in division of 1 upon 4 pi r square. So here it is r square, here it is r cube. So the things remain would be only the r. This is equals to q by, here it is, this is the thing. Here it is the q by 4 pi epsilon naught multiplied by r divided by r. Look at this. Here this depends on the distance r. Here this depends on the distance r. Here E is directly proportional to the radius r. When we are, this is the relation when we are talking about the electric field due to non-conducting sphere when point P is lying within the surface. Now, can you plot this situation? Can you think this as a very carefully? Can you plot the situation? This is electric field. Let's say this is distance r. Don't, don't compare this with the radius. This is not a radius. This is a distance from the center of a sphere. If I split this, this is a distance where radius r would be there. Now you need to plot this. Think very carefully. Think this very carefully and tell me how you can plot this. How you can plot this. What could be the situation? What could be the situation? Tell me. Can you see this? E is directly proportional to the R. Up to what distance? This will go. That this is the sphere. This is radius R. A certain term is within the R and other term is after the R. So I can know is that when I will travel within the sphere, I will travel within the sphere. That means up to the radius r, I am having a relation with directly proportional to the distance. So it should look like this. E directly proportional to the r, and this will continue until the distance is radius r. This is E directly proportional to the r. Is it done? Okay. Next thing. Now, when I am moving outside the surface, when I am moving outside the surface, what would be the relation? Look at this. This is the relation. E would be is equals to kq by r square. This is E directly proportional to the 1 by r square. That means as distance increases, electric field will decreases. So I need to plot this as, it should look like this. That after the radius r, it would look like this. This is 1 by r square. Are you sure? Are you sure? Can you do this? Can you do this on your own? Very good. Next, you just remember this graph. This will help us a lot. This will help us a lot. Now, I want to plot the graph. I want to plot the graph for this situation as well. This is the situation when point P is outside the object, and this is the case of the spherical shell, or you can say a conducting sphere. Look at this. I already plot the graph. What was the situation? Now you know that electric field inside the conducting electric field inside the conducting sphere or conducting shell would be a zero. So look at this. 0 to R, it would be having a zero electric field. 0 to R, it would be having a zero electric field. And when you move to the outside the sphere, when you move outside the sphere, it is directly proportional to the 1 by R square. So as soon as distances increases, this will decrease. So things would look like this. Now, have you done all these things? We have done up to the two tasks or two primary tasks. One, we have derive a relation for the conducting sphere or shell, and another relations are for the non-conducting sphere. Now let's summarize these 2 points only. Now let's before go through the numericals, let's summarize these points. That one is the conducting sphere, or you can say spherical shell. Both are having the same results. Electric field would be equals to k q by r square. I'm talking at this point when r is greater than r. Electric field will be equals to k q by r square when this is r equals to r. And electric field will be equals to 0. I'm talking about the r less than r. So inside the spherical shell or inside the conducting sphere, the electric field will be a 0. Now let's talk about the non-conducting sphere. Electric field will be a kq by r square when we are at r greater than r situation outside the sphere. Electric field will be equals to kq by r square when we are at r equals to r, we are on the surface. And electric field will not be a zero. Please, electric field will not be a zero. It would be a kq multiplied by r. This r would be the distance from the center of the sphere divided by r when r is less than r. Only this reason is different of both the situations. Other things, other things are remains the same. Yes. Now, one very critical point. In first situation, you have been given conducting sphere. You are using the rules of the conducting sphere. In second situation, let's say you have been given a non-conducting sphere and you are going to use the rules of non-conducting sphere. But in certain situations, they have not going to provide you that whether the sphere or is conducting or non-conducting. Then in this situation, by default, I hope you understand what the default is. By default, you need to consider non-conducting sphere. This is the default situation. That means if they have been asked that a sphere is there, you need to understand that this is non-conducting sphere. They are not going to tell you anywhere. So, but if they have mentioned it is conducting, very good. Use a relation of conducting sphere. If they have mentioned it is a non-conducting sphere, very good. You are going to use the rules of the non-conducting sphere. But if they have not mentioned anything that whether it is a conducting or it is a non-conducting, then you are going to use a rule by default. It is of non-conducting sphere only. Are you sure up till this? Are you sure? Okay, let's move to the numericals. Let's say that a spherical shell is there. This is a spherical shell. And let's say, non-conducting sphere is there. This is non-conducting sphere. And radius of spherical shell is r. Let's say r1. Radius of this sphere is in r2. I have given the charge of q1 to the spherical shell, and I have given the charge of q2 to the non-conducting sphere. Have you done up till now? Can I say something more? Okay, let's begin. You need to find out electric field at this location. This is location 1 and its distance is A. You need to find out electric field at this location. This is location number 2 and its distance will be B. You need to find out electric field at this location. This is location 3 and its distance would be a C. So what they have given is that find out electric field at 1, 2 and 3. Now how can you do this? Tell me, how can you do this? Let's say I need to find out electric field at first location. Electric field at first location. So I need to re-examine the situation at first location. Which are the objects which will give me an electric field? I am having a two objects. One is the non-conducting sphere and another is the spherical shell. One is the non-conducting sphere and another is the spherical shell. Location A. Location A is inside the spherical shell. Yes or no? Yes. So according to so I need to consider like this. E1, it's an electric field due to spherical shell plus electric field due to sphere. Now for the spherical shell, this point is within the sphere and spherical shell having no electric field within the sphere. So this is 0 plus plus electric field due to sphere. Now consider re-examine the thing. For the sphere, this is an insider point. And when the point is inside, what you need to do is you need to write an electric field such as E, that is the K, multiplied by Q2, it's a charge, multiplied by distance from the center, it's an A, divide by, divide by your radius. The radius of non-conducting sphere, it is R2. So this should be R2 cube. You understand the situation? Yes? Are you sure? Well done. Now have a pen and paper and do this with me. Now we are talking about the E2. It's the second point. It's the second point. So what I need to do is I need to again find this electric field due to spherical shell plus electric field due to sphere. Now, for the spherical shell, this is this point number two. This is point number two. Look at this. This point is away from the spherical shell. And when the point is away from the spherical shell, you are having a relation of kq by r square, where r is r where the distance. So you can write like this. It's a k q. You are having a charge q1 divided by distance. It's a b square. Now again reconsider the things for the sphere. It's a non-conducting sphere. It's a non-conducting sphere. And point two is within the sphere. Point two is within the sphere. So what you need to do is you need to consider an electric field when point P is inside the surface. Then it should look like K Q2 multiplied by distance. It's in B divide by radius, or I should say a cube of the radius. So this is R2 cube. This is electric field at location 2. This is electric field at location 2. Now, can you do this for location number 3? Can you do this for location number 3? What is it? E3. I should write it's an E due to shell plus E due to sphere. This would be the situation. Now, what is E due to shell? Look at this. This point. This point is outside the object. It is at this point. It is outside the object. For the shell, it is a k multiplied by q1 divided by square of the distance. The distance is c. So it is a c square. Plus, now for the sphere as well, it is the outside the object. For the sphere as well, it is outside the object. So when it is at the outside the object, and it is at the outside the object, the relations would be the same. It's k multiplied by charge divided by square of the distance. So this is k multiplied by charge, which is equal to divide by square of the distance. It is c square. Yes, if you have done up till this, well done. Great job. Did you understand this complete situation? What we are going to do is we just simply write down electric field due to each and every object individually. I repeat, individually. We are just going to use an electric field due to all this. Are you sure? Would you like to do one more question like this? Okay, let's begin. The situation is this is spherical shell and having a charge given is q1 and the radius is r. I should say r1. This is spherical shell. Another object, another object. It is a conducting sphere having radius of r2. And the third object which I can see is given a charge q3. Given a charge q3, it is non-conducting sphere, and its radius will be r3. Its radius will be the r3. Now, now you need to find out. You need to find out electric field at this is the location number one, and distance is a. And electric field at this location. This is the location number two, and your distance will be the b. So you have been asked that find electric field at one and two. This is the question. You need to find out electric field at 1 and 2. How could you do this? Tell me. Let's begin with the even. Let's begin with the even. So at location A, you should focus at location A only, which all objects will give me the electric field. So I need to write all this thing. That's an E due to shell plus E due to conducting sphere plus E due to non-conducting sphere. Now, E due to shell. This is the location number one. Location number one is outside the spherical shell. So, what would be the relation? To remember quickly, what would be the relation? Yes, you assume it correctly. It's an K multiplied by charge. It's an Q1 divided by square of the distance. It's an A square. Plus, next situation, electric field due to conducting sphere. A location 1, which is at distance A, is within the conducting sphere. It's an inside of it. And for inside of it, there will be a no electric field. So this would be the 0 plus plus. Next is the electric field due to non-conducting sphere. For non-conducting sphere, this is Q3. And this point is lying within the surface. And it is having an electric field. What it would be? Let's write it down. It's a K multiplied by charge multiplied by distance. The distance is A divided by cube of the own radius. Cube of the own radius. And its radius is R3. So this is R3 cube. Have you done it with this? What was your answer? Was it same? Great. Well done. Now let's focus on the second point. It's an electric field at location number 2. Who will give the electric field? All these three. So it would be an E due to shell plus E due to conducting sphere plus electric field due to non-conducting sphere. This would be the situation. What would be the E due to shell? What would be the E due to shell? It is, look at this. This location is outside the spherical shell. So you need to write it's an K Q1 divided by square of the distance. This is B square plus electric field due to conducting sphere. Even this location is outside the conducting sphere, and when the point is outside the sphere, you need to write it as K multiplied by charge. Its charge is K2 divided by square of the distance. It's a B square. Now consider about the electric field due to non-conducting sphere. Due to non-conducting sphere, this point is outside the non-conducting sphere. So again, the things would be the same. So this is KQ3 divided by B square. Yes, this is the correct answer. What was yours? Is it the same? Well done. You learn these things very quickly. Happy for you guys. Okay. So let's wind this up. We have done in this class applications of Gauss's law, and we have chosen the spheres and spherical objects. That means that covers a point charge, that covers the spheres, that covers the two kind of spheres, conducting and non-conducting. We have derived relations for the conducting spheres and non-conducting spheres, and we have gone through the application of it. So just you need to do one thing, that do practice this kind of questions. This will be available in your practice sheets. Plus you need to remember a formula for every situation. While I say every situation, I mean within the body, outside the body, on the body, as well as you need to remember a graph for it. In many examinations, directly a graph has been asked that if location is this, that means if R is greater than R, draw or plot a graph for the electric field versus a distance. Yes, so please do practice a lot. This will help us. Let's shut it down. Thank you. Bye bye. Take care. Goodbye.